Okay, so let's have a look at an example of a trajectory calculation. We have a ball with an initial velocity of 160 feet per second at an angle of 30 degrees with the horizontal. Find its position and velocity after 2 seconds and after 4 seconds. So, as always, first let's draw an axis system so we know what we're talking about. We'll have y vertically, x horizontally. If we have y vertically upwards and x horizontally, then the acceleration due to gravity is going to be downwards, and we show it's downwards by the sign minus. Okay, now before we go any further with this, let's remind ourselves a little bit about vectors. So we have an initial velocity, let's call it v, I for initial, and that initial velocity is making an angle of 30 degrees with the horizontal. We can always resolve any vector into perpendicular components, and in this case let's resolve our initial vector into a horizontal component and a vertical component. The horizontal component we'll call VIX, and the vertical component we'll call VIY. Okay, so magnitudes, VIX will be equal to VI cosine 30 degrees, and VIY will be equal to VI sine 30 degrees. So we have separate motion in the x and y directions, and we will compute that separate motion to find the x and y position and velocity at 2 seconds and 4 seconds, and then we will combine that x and y information back so that we calculate the resulting velocity vector. And let's just think a little bit more about what that will look like before we actually do the calculation. So we have some initial starting vector, vi, and the trajectory will be a parabola. That's supposed to be a parabola. And at any point in the trajectory, the velocity is tangential to the trajectory. So as we are going to neglect air resistance, there is nothing to reduce the velocity in the x direction, which will remain constant at VI cos 30, but the velocity in the y direction is subject to the acceleration due to gravity. So at the initial part of the trajectory, the velocity in the y direction is VIY, but by the time we reach the top of the trajectory, which I'm just marking with a red circle, the y component of the velocity has dropped to 0. And in fact, that if we wanted to find out about the maximum of the trajectory, the fact that the y velocity is 0 at that point would be a condition that we could use to establish what's going on. Okay, so I'm going to take a brief break and then we'll change page and carry on with the calculation. Actually, before we change page, just let's note what the initial velocity in the y and x direction are. This is equal to 160 feet per second times cosine 30 degrees, which is equal to 139 feet per second, whereas VIX is equal to 160 feet per second sine 30, which is equal to 80 feet per second. And also let's note that as we are working in feet per second, we can continue to work in feet per second, but all of our distances will be expressed in feet and all of our times in seconds. And therefore we need an appropriate unit for the acceleration due to gravity, and the acceleration due to gravity has dimensions of length per time squared, which in this case will be feet per second squared. Okay, so now we've done that, let's move on. Okay, so we still have left to do the vertical displacement at 4 seconds, and we can fairly easily do that. So y at 4 seconds is equal to 320 feet minus 256 feet, which is equal to 64 feet. Okay, so we've done the position coordinates, and now we need to calculate the velocity coordinates. So we want the velocities at 2 seconds and 4 seconds. The x velocity is the easy one because we know that Vx at 2 seconds is equal to Vy, is equal to Vx at 4 seconds, which is equal to the initial x velocity. In other words, the x velocity remains constant, doesn't change with time. For the y velocity, we need to use the equation that the velocity at a particular time is equal to the initial velocity in the y direction minus gt. So in general that equation would be v initial plus at, but here a becomes minus g. Okay, so all we need to do now is substitute in the numbers. So Vy at t equals 2 seconds is the initial velocity in the y direction, which is 80 feet per second, minus the acceleration due to gravity, 32 feet per second squared, times 2 seconds. And if you work all of that lot out, you'll find that that is equal to 16 feet per second. And similarly, we can calculate the velocity in the y direction at 4 seconds, being equal to minus 48 feet per second. So the important point to note here is that after, in the case of t equals 2 seconds, the velocity is upwards. After 4 seconds, the y component of the velocity is downwards. Now, in a certain philosophical sense, we've actually solved the problem that we were asked to solve, because we have calculated 2 points on the trajectory. We've calculated a point at 2 seconds, where the vertical height was, I think, what was the vertical height? 96 feet. And after 4 seconds, we know that the vertical height was 64 feet. And so we know the height and we know the distances. So we know the x components of those two from our very first calculation. We also know the x velocity at both points, which does not change, and we know the y velocities at both points, which does change. So we have coordinates that tell us the x and y value of this point and the x and y value of that point, and we have vectors that tell us the x component and y component of the velocity at this point and the velocity at this point. However, in the spirit of the question, we're asked to find the vectors and the displacements, and what we're actually being asked to do in that case for the vectors is find the magnitude of the vectors r and the two angles, and I'll label them both by theta, but this is theta at 2 seconds and this angle is theta at 4 seconds. Similarly, we're being asked to find the displacements, and the displacement is given by a distance d and an angle, and just for variety I'll call the angle phi, and we will have a separate, although this is going to get very messy, we will have a separate displacement with a distance d at 4 seconds and an angle phi at 4 seconds. Okay, so because you saw me draw that, the diagram hopefully makes some sense. So to calculate these, we will need to use the Pythagorean theory 4 times, twice for the distances, twice for the vectors. And we will need to use tangent of an angle is opposite over adjacent, and inverse tan to find the angles that we want. So that's what we'll do next.